Hi everybody, Augie Kennedy here, back with super awesome calculus. Well, we're on chapter 5, which is about the fundamental theorem, where we've been talking about integration. We outlined so far what the idea of finding an area under a curve. We explained that as a definite integral, and then by introducing the fundamental theorem of calculus, we realized that basically to find an integral, you need to find antiderivatives of a function. Last time we talked about indefinite integrals. Big difference. Indefinite integrals, which are just general integrals with no bounds. Now I'm going to sneeze. One sec. Maybe not. But also, guess I am. Anyway, also, there's a thunderstorm, so if there's a lot of thunder, that's what it is. Anyway, God, I keep sneezing. Anyway, last time I left you with a big problem, so to speak, that had to do with the net change theorem that we looked at last time, and the problem read as such. The marginal cost of manufacturing X yards of a certain fabric is C prime X equals 3 minus 0.01 X plus 0.000006 X squared in dollars per yard. Find the increase in cost if the production level is raised from 2,000 yards to 4,000 yards. Well, you'll be able to do this if you remember the net change theorem, which said that big FA, or big FB, minus big FA equals A to B F prime, big F prime X dx. This is pretty easy to see. It's just a permutation of the fundamental theorem of calculus. Now right here, we have big FB, it's 4,000 yards. So this is saying that F 4,000 minus F 2,000, the change, is going to be equal to the integral from 2,000 to 4,000 of F prime X, which in this case is C prime X, which is 3 minus 0.01x plus 0.1234506 x squared dx. That's what the net change theorem tells us. So all we need to do is solve this integral. And we can do that fairly easily using the tricks we learned. The integral of 3 is 3x minus 0.01 x squared over 2, which is really 0.005, right? Yep. Times x, x squared, plus we've got 5 zeros divided by 6, followed by a 6, x cubed over 3. The 6 and the 3 cancel out, and we get a 0, 1, 2, 3, 4, 5, 2 x cubed. And we're going to evaluate that at 4,000 and 2,000. If you do that, if you evaluate it there, you'll get, for the first part, 12,000, 4,000 times, if x is 4,000, 3 times 4,000 is 12,000, minus plug in 0.005, 4,000 squared gets you, wow, 0.005, 4,000 squared would be 16 million, yep, 16 million plus 0.00002 times 4,000 cubed, which is 64 billion, 1, 2, 3, 1, 2, 3, 1, 2, 3. And we're going to subtract the value at 2, which is going to be 6,000, minus 0.005. 6,000 cubed is or 2,000 cubed is 4, or squared is 4 million. plus 0.0000002 times 2,000 cubed is going to be 8 billion. 1, 2, 3, 1, 2, 3, 1, 2, 3. If you do all of that, if you do all the arithmetic there, you'll find that you're really just looking at 60,000 minus 2,000, which yields 58,000. And since we're talking about the cost, the increase in cost, the unit of cost is dollars. So there you go. The answer is $58,000. Now today, we're going to be talking about the substitution rule. It's pretty, I think this is a pretty interesting rule, and you'll find that it's going to be very, very, very useful in figuring out integrals. Now, because of the fundamental theorem of calculus, it's very easy for us to solve integrals like the integral of 2x, for instance. Well, the integral of 2x is just going to be 2 times the integral of x, which is 2x squared over 2, which is x squared. That's really easy. We can even do things like the square root of x integral. I mean, that's really just saying x to the 1/2, and we can raise that by 1. X to the 1/2 plus 1 is 3/2 over 3/2. We can figure out all of those types of integrals. We can even figure out inverse trig integrals. Dr. Pepper Cherry, always a good decision. Till you get kidney stones. Anyway, we have a way to figure out a lot of integrals. But let's say we get an integral like this. The integral of 2x times the square root of 1 plus x squared dx. Well, the square root of 1 plus x squared doesn't appear in a denominator, so we don't have any inverse trig functions we can use, and we've got a product. So this creates kind of a problem here, because the integral of 2x times the integral of square root of 1 plus x squared isn't really going to, it's not going to work, and also that's not necessarily square root of 1 plus x squared isn't necessarily going to be the easiest integral in the world to find. So what we use here is we use an interesting idea called substitution. Now substitution has its roots in the chain rule. What we're going to do, if you remember the chain rule from derivatives, if we've got to differentiate f g of x, we take f prime g of x and we multiply by g prime x. Okay? That's pretty simple. But with a derivative, or with an integral, let's say we have f prime g of x times g prime x. If we take the integral of that, we're going to get f of g of x plus c. You see, the inverse of the chain rule will give us a composite function, and that is the substitution rule. The substitution rule explicitly, let me explain this to you, as the book says, if u, I'm going to introduce a new variable, u is g of x, and if u is differentiable and its range is in the interval and f is continuous, in other words, as long as it doesn't violate any basic rules that we already know of differentiation and integration, u equals g of x, then the integral of f of g of x times g prime x dx equals the integral fu du. Okay? So the concept here is fairly simple. Let me break this down. Step 1, analyze the integral. Is it something that we easily know? Is it like a basic function like x squared, or sine, or cosine? Or does it have 2 parts to it? If it has 2 parts to it, move on to the next step. We might want to try substitution. Substitution says the integral of the composite function f prime f of g of x times the derivative of g of x is going to give us f u du. So we've got to find what g of x is. Okay, we've got to find what g of x is, and we've got to find what f prime, or what g prime x is. So we've got to make a guess here. The guess that you'd want to make, I'll help you along, you might be able to see it, and this will be easier once you see it in practice. We look at this function. Well, the derivative, let's say this, let's call this f, or let's look at 2x first. We've got to find the derivative. Is the derivative of 2x somewhere in the function? Well, the derivative of 2x is 2. Doesn't really help us. Let's look at the square root. Well, the square root would be x to the 1/2. And we don't really see a 1/2 x. That's kind of messy. All right, but let's look at what's under the radical. 1 plus x squared. What's the derivative of 1 plus x squared? Well, it's 2x. Interesting. So the derivative of this part, the 1 plus x squared, does appear right there as 2x. So let's go ahead and make a substitution. Let's let u equal 1 plus x squared. All right, that's all well and good. But we also have a dx to contend with. All right? Well, dx, we want to go from dx to du. Because remember, the substitution is f of u du. So we've got u equals 1 plus x squared. Du is going to be the derivative of 1 is 0. The derivative of 2x is 2x, but we're differentiating with respect to u, so we still have that dx there. So it's 2x dx. Now we can see that we've got the 2x, we've got the dx, we've got the 1 plus x squared. Watch how we can rewrite this now. We can take the integral of the square root of u du. They're the same thing, because we've got u is this, and we've got du is this. So all we have left is square root of u du, and we do know how to integrate that. That's going to be u to the 3/2 over, right? Yeah. It's going to, yeah, it's u to the 3/2 over 3/2, but they write it 2/3 u to the 3/2 plus c. Okay? That's the function. But we're not quite done yet. Because now we have to go for, because it didn't ask us what the integral was in terms of u, it asked what it was in terms of x. Well, that's easy. We just plug in x where u is. U is 1 plus x squared, so the final answer is, it's going to be, 2/3 times x squared plus 1 to the 3/2 plus c. So we found a substitution, we made it, and we plugged it back in. Let's look at another one really quick, just so we can get the idea. We've got the integral of x cubed cosine x to the 4th plus 2 dx. We totally don't know how to deal with that. But we can look and we can see x cubed and we see an x to the 4th. So we can tell that there's going to be some way, perhaps, that we can make a substitution that's going to get rid of this x cubed and get rid of that dx and replace it with du. Well, you might be right if you choose u to be x to the 4th plus 2. Well, that would make du 4x cubed dx, or du in terms of dx would be du over 4 equals x cubed dx. So, what this is really saying is that this integral is equivalent to the cosine of u, which is, because u is x to the fourth plus 2, du, but remember, we've got du over 4. It's 1/4 du. But 1/4 is just a constant, so we can take it outside of the integral. So it's 1/4 times the integral cosine u du. Well, this is really easy as well, because the integral of cosine, as I hope we know by now, is sine. So it's 1/4 sine u plus c, or 1/4 sine x to the fourth plus 2 plus c. You see how we did that? Just plug the x right back into where u was, and we're good. All right. So that's the idea behind substitution. But substitution has, it's got some fairly, oh, by the way, there's one other integral that I want to introduce here. Don't really want to prove it right now. But just so you know, using substitution, you can find tan x dx. The integral of tangent is the natural log of the secant of x plus c. You can find that by rewriting tangent as the integral of sine x cosine x dx. Actually, this is a pretty decent example. Sine x over cosine x dx. Well, let's let u equal, what do you want to make u? Let's make u equal, yeah, of course, cosine x du is negative sine x dx. All right, so now we've got the integral du over u negative. All right, and then we integrate that, and we get negative natural log of u plus c, which is negative ln, the absolute value of the cosine x plus c. But using the law of logs, we realize that negative ln cosine x is just ln over 1 over cosine x, which is the secant, which is why this integral is the natural log of the secant plus c. All right? Now, this idea of substitution works really well with definite integrals too. Here's a pretty good example. We've got, I'm going to show you how this works. The idea is that if we've got a to b of f of g of x, g prime x, that's going to be equal to g of a, g of b, revalue the endpoints, fu du. So you've got to do a little extra step with the definite integral, but it's not that hard. So for instance, let's say we have this integral right here. We have the integral from 0 to 4 of square root 2x plus 1. Okay? Well, right away we're going to know that we're going to want u to equal 2x plus 1, du equals 2 dx, so du over 2 equals dx. So we're going to have a half on the outside. But here's the thing. Here's the key observation to make. The key observation is that we're not going to be from 0 to 4 anymore. We've got to find out what u is going to be when x equals the endpoints. So what is u when x equals 0? Well, 2 times 0 is 0 plus 1. So we've got 1 as the bottom point. What about 4? 2 times 4 is 8 plus 1 is 9. So the new integral is going to be valued from 1 to 9 of 1/2, or 1/2 on the outside, square root of u du, or u to the 1/2. And we know how to integrate that. That's going to be 1/2 times 3/2 u to the 3, or 2/3 u to the 3/2, evaluated between 9 and 1. And if you figure that out, it's going to be 1/3, 9 to the 3/2 minus 1 to the 3/2. It's going to give you 26/3. So that's how we can find a definite integral. Definite integral just means all we need to do is one extra step from the indefinite integral. Once we get our u, and we get our u in terms of x, plug in the endpoints of x to find out what the new u is. All right. Now finally, the last part of substitution, I mean, you can prove this theorem via substitution. It doesn't necessarily use substitution, but these are just some interesting things that you might want to know. If f is even, all right, if it's even, an even function, then if we've got from negative a to a, f of x dx, this is the exact same thing, and this makes intuitive sense, as 2 times the integral from 0 to a, f of x dx. I mean, if we're trying to figure out x squared, which is an even function, wow, that was bad. X squared, even function, that's a little better. This, if this sums to 3, I don't know, then the left side is also going to sum to 3. So it's just going to be 2 times one side. Makes sense. That's an even. If f is odd, then from negative a to a, f of x dx equals 0. This makes sense too. Let's use our most basic one that we like to work with, is x cubed. If this area is 3, well, this area is going to be negative 3. And they're going to balance out and create 0 if this is a and this is negative a. All right? So that's what it says. If it's even, it's going to be double one side. If it's odd, it's going to be 0. So if you see on a test, I know some teachers like to put a really almost impossible to integrate odd function on a test. And I remember I was looking at this function. I tried substitutions because, you know, sometimes substitution doesn't work. I mean, sometimes, let me pull up a nice example of a place where substitution isn't going to work. Here you go. E to the x sine x. You need something called integration by parts, which you learn in Calc 2. If you have a function like that, there's not really a substitution that you can use that's a part of the other function. Now that particular function doesn't work because it's not odd. But if you see a crazy function and nothing works, check to see if it's even or odd. If it's odd, you know the integral. If it's from like negative 2 to 2 or negative 5 to 5, it's going to sum to 0. So that's everything you should know about substitution. And I've got a fun big problem for you to solve. The integral that I want you to solve is, or evaluate, is the indefinite integral of x times the quantity x squared minus 1 cubed dx. Use substitution, look at that function, see if there's a part that you can use, and go with God. Next time we're going to have a test. So be ready for the test next time. It's going to be all on integration and things we've learned. And I look forward to seeing you then. Till next time, take care, y'all.